C++ provides the common basic floating point types. Here I have a working copy of floattypes.cpp from Chapter 5 of the exercise files. C++ provides these floating point types, float, double, and long double. And if I just build and run this, you'll see that these are all actually different sizes. The float type is 4 bytes, the double float is 8 bytes, and the long double float is 16 bytes. Literal floating point numbers are indicated by having a decimal point. So if I say 500.0, that's a literal floating point number. I can do the same thing with scientific notation, and I can say 5e2, and I get exactly the same value. I'll go ahead and print that value out. Printf float f is, and I'll say %f for a floating point number. And now when I build and run, you see that the value is 500, and I've indicated it here with scientific notation. It's important to understand the distinction between scale and precision when you're working with floating point numbers. Scale is how large or how small a number may be represented. Precision is the accuracy of the representation to a number of significant digits. What this means is that when you use floating point numbers, you may get rounding errors. And so I'm going to go ahead and show you an example of this. I'll say f equals 0.1 plus 0.1 plus 0.1. Now we would expect the result of that to be 0.3. I'll go ahead and remove these so we don't get a warning. When I build and run, you see it says that the value is 0.3. That's the result that we would expect. But here's the interesting part. If I say if f is equal to 0.3, puts true, else puts false, we find something interesting. The value is not actually equal to 0.3. And we can find this out by printing it out with a larger precision. I'm going to print it out to 10 significant digits, and we see that out here we have a little bit of a rounding error. So while it may be possible to represent very large and very small values using floating point types, the precision of these types is always limited. Now you get more precision with the larger type. So if I make this a double float, it's represented by a larger space, and so it can represent more precision, right? And actually we don't use the float keyword there. We just say double, and this is a double number now. And now when I build and run, you'll see that we get even more precision here, but it still says false. And if I increase this to say, well, we'll increase it to 20 digits, and now you see that our error is just out farther, but there still is a rounding error. So on most modern systems, float is 32 bits, which is a precision to about 7 digits. Double is 64 bits, which is a precision to about 16 digits. And long double is either a synonym for double, or it may be an 80-bit IEEE floating point format. The precision is going to vary. What's important to understand is that while it's possible to represent very large and very small numbers with these types, it is always at the expense of accuracy. And if precision is important, as in the case of accounting where you're going to want no rounding errors whatsoever, then you'll want to use an integer type instead.